Thank you. Okay. So I am going to discuss driven-dissipative quantum dynamics of Heisenberg spin-half chains, and this work has been done in collaboration with Pooja Mansi, who is also at Raman Research Institute, and our paper is available on arXiv. So I will begin by briefly introducing Heisenberg spin-half chain. And mostly I will talk about a version of Heisenberg spin-half chain, which is known as XXG spin chain. So this model of the Heisenberg spin chain I am going to talk today is with nearest neighbor exchange interaction between quantum spin half, and in the case of XXG model, we will have the exchange coupling Jx for the x and y component of the spins can be different from those of the z component of the exchange interaction. And also I will have one external magnetic field H along the z direction of the spin. And as I am talking quantum spin, I will have the spins half are represented by Pauli matrices, which have this kind of commutation and anti-commutation relations. And the phase diagram for the XXG model can be represented in a plane, on a plane with delta, the anisotropy parameter, which is the ratio between Jg and Jx coupling, exchange coupling, and the external field H. So if I consider first H equal to 0 or no external field, then for the XXG model, I will have three different phases. For delta less than -1, the spins will try to align themselves in the same direction. So the ground state will be a ferromagnetic ground state. And for delta greater than 1, the spins will try to align in the opposite direction. So the nil state will be a antiferromagnetic nil state will be a ground state. And between -1 and 1 of the value delta, I will have an XY phase. And this is a disordered phase where the spins in the z direction are random. So now if we can extend this phase also in the presence of external field, and the phase will look like this one. And one particular feature of this phase diagram, that if I make H to -H, there is a reflection symmetry of this phase. So I will mostly consider actually -H value or the +H here because of some physical motivation, which I'll talk later. So now the model which I just showed you before, here I just changed the sign plus, and I'm talking this spin chain with for let's take n number of spins, and I do a transformation in terms of raising and lowering of ladder operators, and then the Hamiltonian looks like this. And one particular feature again here, that when I transform, the bulk part here has different coefficient like H-4jg compared to the two boundary. And for simplicity of this talk today, I will actually switch H-2g in the two edges to H-4jg. So the model which I will mostly consider is this one, where I have the exchange coupling in the x direction, the z component, and also the local fields, which is like scaled by 4jg. And I am interested to drive that system, the XXG spin chain, to non-equilibrium, and we can do that by applying a time-dependent magnetic field, for example. But I am interested more in open quantum scenario, so I will couple this XXG spin chain at the two edges with two zero temperature radiation field baths, which are at different energy density. So because of different energy density, there will be energy flow through the system from one bath to the another bath, and that I will call a driven-dissipative quantum system. And the bath which I'm considering here are very simple. They are harmonic modes created by annihilation, created by AK Dagger operator with some energy dispersion VGK, which is also linearized as you see here. Vg is the group velocity, K wave vector, and I have left bath and right bath. They are similar, only I have changed the operator. But And also I have used some coupling where you can think like when I annihilate one bosonic modes in the left bath, I can excite or I can flip the spins in the first side. And similarly for the right bath on the last side. And I couple this bath with the system at time t equal to t naught, and before t equal to t naught, or just at time t equal to t naught, my state of the full system is represented by, for the left bath, a coherent state. For the right bath, I keep it in vacuum, and for the system, I take this kind of like, which is like spins are pointing down, but actually in the steady state, the initial state of the system will not create any difference. So the coherent state has property like if I act the annihilation operator of this left bath on this coherent state, it will give, means it's an eigenstate, so it will give my eigenvalue kind of EP with the constraint that the energy of the mode of that harmonic oscillator mode or bosonic mode has to match with my coherent state frequency, and that constraint is given by this delta function. So what I will do in the formally or in the work which I am presenting here, I will time evolve from this initial state using quantum Langevin equation method, and I will try to look both transient and steady state dynamics of the full system. And to do that, we have developed a kind of a description where I can calculate any time order correlator from this tensor products matrix in ensembles. So I have like every side's spins are represented by sigma daga sigma and sigma 1 daga sigma 1, which is like you can see like it's sigma x y z, the some that representation in terms of ladder operators, and also I have unit matrix. So I will time evolve the state from the initial state psi t naught, which is I showed you here, and I will not talk about how I do that thing, but let me say a little bit what is the physical motivation of doing these things. So the motivation is like I can create a Heisenberg spin chain, or not I, means experimentalist can create an Heisenberg spin chain with atomic medium where the atom, you can think some real atoms like rubidium or artificial atoms like some superconducting qubits, and this system can be thought like a highly nonlinear medium for light. And what I will do, I will drive these systems with this laser, which is very tightly focused to really behave like a 1D system. And in these systems, what we are considering, that left bath is like the laser which I incident from the left, and I'm interested to calculate radiative energy transport through this medium. And mostly today's talk, I will consider how much light power has moved from left to right. And that we can calculate. Okay, so first of all, what is the power I incident from this coherent state is something given by the amplitude square by 2 pi Vg square, where Vg is the group velocity. And if I increase EP, that means I'm driving the system highly, and that high driving is determined by something that the driving rate, will it be higher than the coupling rate or the broadening due to coupling. So broadenings are presented by this kind of gamma A R, or a similar expression I can write for gamma L, which is nothing but the square of the coupling amplitude, which I showed in the previous page. This coupling, GR, coupling rate, sorry. And the transmitted power, which I'll calculate in this problem, is can be calculated from this expression. So I am doing everything within Heisenberg picture. So what I need only to calculate time evolution of operators, and as I said, that I can calculate using just a quantum Langevin equation method, and I will calculate that quantity here in the initial state expectation. And let me summarize my main result. So the main result, what we have got here, and I will just say for particular some interesting regime. So if I have a resonant driving, which means like the coherent state which I am signing from left is means its frequency is equal to h minus 4 jg, And if I drive is really large, which I will call a nonlinear regime, and I'm doing everything at 0 temperature, so then the result, we find that tau nt, which I defined as like transmission coefficient for radiative energy transport, is non-monotonic function of this anisotropy delta, which is ratio of exchange coupling Jg by Jx for a finite length chain. And we also see that when delta is 0, which is xy model, and delta very large, which is like the Ising limit, in both these two cases, the transmission is independent of n, which can be called like ballistic transport. And at delta near 1, we see that tau and t in the steady state, so t infinity means the steady state, strongly depends on n. So it's some kind of, it can be anomalous or diffusive transport near delta 1. So there are not many studies along this direction for radiative energy transport in quantum Heisenberg model in open quantum system, but there are few studies along this open means for the spin transport in open quantum systems, for example, studies by Zinderich and his collaborator Posen. So their result in the linear response spin transport regime at infinite temperature, for example, if I take external field 0, is ballistic when delta is smaller than 1, which seems to match with the radiative energy transport result also. But now they have diffusive transport for large delta, which in this case I do see is also seems to be ballistic. And delta 1 spin transport seems to be anomalous, which I cannot conclude at least from my result for small systems. So now let me show you how I conclude all these things from few figures. And as I said, I will call that if the driving power is small, okay, maybe I go to the then, okay, so I just show you that transmission coefficient scaling with n, and this is what I am showing for different driving power. So that means this is linear regime when driving power is small, and these are nonlinear regime when driving power is high. And in linear regime, irrespective of delta value, I always see ballistic transport because tau n is independent of n. But now in the nonlinear regime, if you look here, the delta 0, which are pink color, they look again ballistic, independent of n. And also delta large, which is 3 here, the blue, no, not blue, yeah, blue, what is this color? Yeah, kind of light blue or deep blue. So this at delta large also it is ballistic, but delta near 1, it seems to show a strong independence, which though it seems from here that it may saturate, but actually we have seen that if I increase the driving power, it does not saturate. So in fact, the coefficient, if I call that tau n scaling with n as n to the power minus kappa, so the kappa coefficient actually becomes larger and larger as I drive. So it seems that it will not saturate at delta close to 1. So the summary of my presentation, that we have generalized the quantum Langevin equation approach to study non-equilibrium transport in 1D interacting open quantum lattice models. We have studied radiative energy transport in Heisenberg spin chains, and we have seen some interesting features of nonlinear transport coefficient at 0 temperature. And the things which we are trying to do in near future are like application of this same technique for other 1D lattice model, for example, this popular Kitaev model for topological superconductors, for spin transport. And we also want to compare our Langevin equation method with the technique developed by Posen for using Lindbergh theory and matrix product operator unsearch. And we are also interested to know how the inelastic scattering happening in this nonlinear medium, so that can be calculated if I can calculate power spectrum of transmitted and reflected particles. And main challenge currently that all these results though are exact and numerically exact and non-perturbative, both in coupling and interaction, but it's only limited to 8 sites. So I really wish to go longer chain length. And also I want to do for different type of bath, not just 0 temperature bath, but more like finite temperature baths and other kind of things. Okay, thank you.
Thank you. We have time for one question.
I mean, why would you expect ballistic, I mean, when you have an interacting model, right? So you generally should expect either diffusive or maybe worst anomalous diffusion. But
so one thing that delta large has this Ising limit kind of things in this model, and it's probably again integrable. So because of that reason, it may be ballistic. I don't know.
Okay, let us thank the speaker.